Okay, after we introduce the electrochemical kinetic, we can derive the kinetic equation of electrochemical reaction, and we can simplify under kinetic control to this Bartholomew equation last time we have mentioned. Of course, you can use the general equation that if you need to deal with the mass transfer case, then you need a general kinetic equation that we mentioned in the last lecture. But today we just want to extend this idea to different application. Of course, we also introduce, once you have this kinetic equation, we can extract the kinetic parameter like exchange current, I0, or exchange current density, or alpha transfer coefficient, like this alpha transfer coefficient, or I0, from either from Tevor probe, or you measure at the data near the equilibrium condition, you can extract the I0. So if you have one data set, you can use a Bartholomew equation or use a general equation. You can get those parameters. But today we want to introduce, if we get this polarization curve, last time we mentioned this polarization curve need to be obtained at the steady state condition. So you need to make sure your data is obtained at the steady state condition. So you get the current burst, this potential or overpotential. So this we call polarization curve. The main idea, you need to make sure your experimental condition can reach the steady state. Otherwise, the data we cannot call it as a polarization curve. So once you have polarization curve with this current against the potential, we can transform this. This curve to this curve. So you just change the coordinate. So we can change the x coordinate at this figure, change to y coordinate. And then the current, we just take a log, or you can also take a natural log, absolute value of the current, because in the log you cannot have a negative value. So if we transform this polarization curve to this curve, actually the same data, we just transform to a different diagram. So if you take the red one for this part is for reduction reaction, you will get this part. Okay? So this is the equilibrium condition, the potential you measure at the equilibrium condition. So this equilibrium potential, that will be here, this equilibrium potential. So this part would represent the the reduction reaction, and this part would represent the oxidation reaction. So you can see if the potential higher than the equilibrium potential, you will try the oxidation reaction. If the potential lower than the equilibrium potential, you will try the reduction reaction. you also know this eta will be less than 0. In this region, eta will be larger than 0. So by the definition of the eta. So then what we can, why we want to use this event diagram? Of course, we to recognize the contribution of event, because this is very important diagram in kinetic application. So that later you can see. So that so this potential actually represent, in this case is at the Euclidean condition, but it's not always at the Euclidean condition. In this case, the oxidation reaction, like this oxidation reaction, is just a reverse of reduction reaction. So this is just a reversible reaction. So if this is a reversible reaction, then this potential we can call as equilibrium potential. But later we will give some example. The oxidation is not a reverse of the reduction reaction. Then we cannot call it as equilibrium potential. That we will introduce later. So as I mentioned, then in the environment, you may have different reaction. So like in this case, this example, we have lead contact with copper. That's what happened. So if these two metals contact together, so if you consider the copper, this copper equilibrium potential, so you can do one polarization curve of the copper. So you get one polarization curve, like this curve I just mentioned for copper. But you can also perform one for lead as well. So you get two curves, then you can transform to this event diagram. So you get this diagram. So as I mentioned, this equilibrium potential of copper reaction, copper reduction or oxidation. Then this oxidation of the copper. This copper ion reduction. So that is event diagram for copper. However, for the lead, this is lead reduction, and this lead oxidation. Okay, so that this just so in the nature environment, if you have copper and lead, last time we mentioned the copper equilibrium potential is higher than the lead equilibrium potential. So electron will go from the low potential to higher potential. So in that case, the copper ion will be reduced. So, but the lead, because lose the electrons, so lead will be oxidized. So that's the case if you contact make a contact between copper and lead, will cause the corrosion of the lead and reduction of the copper. That we call galvanic corrosion. So if you put the two metals together, the one with the lower potential will be corrode. The one with a higher potential would emit, so that we maintain the couple status. So that is the case. So in this case, the dead would dissolve, but couple ion would be reduced. So that called carbonic corrosion. This carbonic corrosion, if you put two element, two metal or two elements together with different potential, one with the lower potential will be oxidized, and another potential, another metal will be maintained. So, and what's the rate? So you can see if you extend this polarization curve, right? This oxidation of the lead and this reduction of the copper ion. Suppose at a steady state, this reduction rate should be equal to oxidation rate, because electron release from this should be equal to the electron received by the couple, so that we get this intercept, means the oxidation current, this the IA, right? The oxidation current is equal to this IC, the couple reduction current, at this condition. So this potential we obtain at the electrode surface. So with the two current, one is oxidation current, IA, one is the reduction current. Both are equal but in different direction. So that's very similar to at the equilibrium condition. We have IA equal to IC, that we call I0. But in this case, and that is at the equilibrium condition. But in this case, we cannot call this equilibrium condition, because it's a mix. So one oxidation is not a reverse of the reduction relation. So we cannot call this equilibrium potential. We call this a mix, or couple potential, or mix. It's mixed potential. Mixed potential. Because this potential obtained is from two different reactions. One is lead oxidation, one is for couple reduction. So we get this potential. So this potential is not an equilibrium potential. It's just a steady state potential, or the current is a steady state. This potential. And we can also get the current. So if in this case, right, if at the same reaction, this we get the intercept. This is what we call I0. But here we cannot call this is I0. I0 means the exchange current density should be at the equilibrium condition. The oxidation current equal to reduction current. So the net current is equal to 0. But in this case, the net, although the net current is still 0, but this current we cannot call as exchange current. This we call I mix, or I corrode. I corrosion, because, or I mix, because There's many application in corrosion application, like this figure. So this in corrosion application. We study the alumina corrosion at a different electrolyte. So you can draw this. Still not. This just put this at the x-axis, y-axis. So put this log I at the y-axis, this at the x-axis. So that you can see this potential is you obtain is E mix or E corrosion. So this E corrosion potential, alumina corrosion. So you can see at the different case, you get and this is, so this we call E corrosion. Okay. And you can also get the current, the intercept of the curve. You can get like extend. You can get the current. So this is we call I corrosion. So we can get the current the same, right? You can get the current from the intercept. You can get the current. So a different current. So the higher current means the corrosion is more serious. If, like in this case, you get a lower current, right? So this condition, the corrosion is less. There's 10 power to minus 8, this is 10 power to minus 5. So this corrosion is serious than this one. And the E corrosion is higher in this case. So if the potential, the E corrosion is higher, means material will be more stable. So you can see from this summary, this is the corrosion current, corrosion rate would increase. Corrosion rate would decrease. This blue one is corrosion. The pink one is corrosion. So the corrosion potential is increased, but the corrosion rate will decrease. So once you add additive, you can reduce the corrosion rate. Okay, so that is very important. So you can see from this SEM image, this without additive, this with additive, this with the FQH, this with HQ. Okay, so but the main idea why want to use this electrochemical method to determine the corrosion rate. If you want to measure corrosion rate, maybe it's very slow. You probably need to wait like 1 year or 1 month to get the loss of the material. So that is not very efficient. But if with the electrochemical method, with this method, you can get the corrosion rate like within half hour or 2 hours. You can get this corrosion rate quickly. So you can evaluate what is the corrosion if you develop a new material, or like we develop a new electrolyte. How this impact on the corrosion rate, you can evaluate or screen quickly, rather than just put the material outside for being a long time. You want to learn the corrosion rate from the weight loss. that is not very efficient. So event diagram is very important, but that is a kinetic. So the E core and the I core is a kinetic parameter. It's not a thermodynamic parameter. It really depends on kinetic of the system. So we mentioned the E equilibrium that need to be reversible reaction. We need to measure at the equilibrium condition. That should be reversible condition. Of course, I equal to 0 because net reaction should be 0. No matter it's this E mix or this equilibrium potential. So I net is always 0, no matter which condition. But for this E mix we mentioned, or for the OCP, open circuit potential, this OCP, okay, or OCV voltage. OCV voltage is more complicated because it involves 2 electrodes. OCP only look at one electrode, so it's much simple. Or E mix, we just mentioned the mixed potential, or E corrosion, E corrosion. So if at the equilibrium potential, I just mentioned this reaction should be reversible. The carboxylation, this should be reversed. Then we can call it equilibrium potential. Otherwise, if this reaction different, like we just mentioned in the corrosion, in the power phase diagram, we mentioned this carboxylation, oxygen reduction reaction. That is 2 different reactions. So that is we call E mix, or you can call, no matter which one, you can call this open circuit potential. So open circuit potential is more general, and the equilibrium potential is more restricted. So the condition, the criteria need to be more in to make sure the reaction is at the equilibrium, it's a reversible reaction. Otherwise, you cannot call it as equilibrium potential. So that I just mentioned. So you can convert from polarization curve, then that the couple oxidation case, like this case. So one is oxidation, one is reduction. So we can draw this diagram. So like oxygen reduction potential is like 1.23. It's higher than the couple like a 0.24. So you have 2 equilibrium potential. This is log I. So you can draw for oxygen reduction reaction. You can study this individually. So this oxidation, this reduction. And for copper as well, this oxidation of copper, this reduction. But in this case, you put the copper and oxygen together, of course, the copper oxidize because the copper potential is lower, the oxygen potential is higher. So oxygen will be reduced, copper will be oxidized. So then you get this intersect, you get this mixed potential or E corrosion. You will get this the case we mentioned in the power phase diagram. So if you have potential at the domain of the carbon corrosion region. That's the case. Okay, then you can get the I corrode, the corrosion current from this. So you can measure the corrosion rate quickly. You can get the corrosion potential and the corrosion rate. But that is very important. So what does it mean of this E-mix? E-mix means if you have environment with oxidant and reductant, then naturally it would form a potential that called mixed potential. That is the potential, the natural potential. So like in this case, you have oxygen and you have carbon together, then on carbon surface you get this potential naturally. Of course, I mentioned this kinetic parameter. It depends on the kinetic. Like if you change the oxygen concentration, this curve will be changed to here, right? So your E-mix will change. Or you change the carbon side, you can also change the intercept. So that is really depend on the kinetic of the system. So that idea give us a very important idea. We can determine the environment condition. That if you remember, I mentioned the CMP. That's also important. You can determine the potential of the CMP solution. Yeah, that is very important. So like in this case, we have a power-based diagram. We learn, right? So this is a carbon corrosion region. This is also carbon corrosion. This is a perturbation. This immuned area. The carbon metal will be stable. This oxygen reduction reaction. This hydrogen proton reduction reaction. Okay, then we have an event diagram. Okay, so we have event diagram. So you get this mixed potential, right? So if we extend to here, you get this point. So this is the potential we mentioned in the event diagram. We measure in the environment the potential. So we know how to measure the pH. We also can measure this potential. Then we can determine this coordinate. Okay? If your pH is here, then you will be at the material will be at the perturbation region. If the pH here, the carbon will be at the corrosion region. If pH is here, also at the corrosion region. So that is very important. You can extend your application from this event diagram. Then, as I mentioned in the CMP, you want to maintain at this region, right? So in CMP, they are not use oxygen; they are use hydrogen peroxide. Like you can use hydrogen peroxide as an oxidant. Then you can control. If you control the solution of the hydrogen peroxide, then you can control this potential at the perturbation region. So that make it easily to polish the surface smoothly. Although there are many conditions that is still very challenging, like what is the slurry, the particle hardness, or the porous paper, what is the condition of the porous web, that you need to have feedback control, no matter in the solution part, but also in the particle or the porous paper condition. Of course, if you can measure the surface directly, then you can feedback to adjust your condition. So as I mentioned, so this E mix is a kinetic condition, depend on the oxygen concentration, and also depend on the substrate. Because the substrate is a catalyst, so if substrate different, then this E mix can be different. Okay, so of course pH you can control, so you can determine the coordinate in the Paul-Best diagram. Then we were to draw this potential drop in different cells. We in the thermodynamics we already draw this. Only consider at the equilibrium condition, no current at the equilibrium condition. So this electrolytic cell, the theta G is larger than 0. So the EC should be, so the theta E cell should be less than 0. So EC must be lower than the EA at the electrolytic cell, but in carbonic cell, just opposite. EC should be higher than EA. So that time we already draw this diagram. This is the potential drop diagram. Actually, it's energy loss of the electron energy loss. But we are familiar with the potential drop. But it's better to always interpret from the energy perspective. So this is the potential drop. Okay, a potential drop at the equilibrium condition. Equilibrium condition is potential drop at the equilibrium condition. So we want to consider if current is not 0, what happened? So if current is not 0, what happened in the electrolytic cell and carbonic cell? So this again is right. We can this for electrolytic cell. Again, we can draw from the energy scale first. Then we can extend to potential scale. That so like in energy scale, the part this energy scale, this potential scale. So as I mentioned, we draw in energy scale is always better. For electrolytic cell, you convert the electric energy to chemical energy. So you consume the energy of electron. So if you originally your energy is like this, right? Originally, this original diagram. But since you want to convert the electric energy to chemical energy, if you want to convert the same chemical energy, since we need to consider loss, then we need to add more energy. So the electron energy will lose more. Not this only for thermodynamic, but you need to include the kinetic loss as well. Then in a solution, because now you want to move the ion transport, then you also need the energy. So you also have a energy loss in a solution part. And again, for this anodic part, the thermodynamic energy, like this value, this only considers thermodynamic. But again, it's similar here. Right? You need to add more energy to drive this chemical reaction to produce the same amount of the D and C. So that is same amount of the B. So this A to B, this C to D. So in total reaction is of course this is the product at the cathode side, this is the product at the anode side. So your energy curve will be like this. Okay. So I can draw so the overall curve will be like this. Consider the loss. Then if you know that, then you can convert this energy diagram back to a potential diagram. So like this original potential, but you need additional potential because additional energy loss. So you get this curve. So this we call overpotential, activation energy overpotential, cathodic overpotential. But in the solution, you also need to consider loss. Okay? And again, for the analytic part, this the potential should be the same as for thermodynamic, but you need additional one. So you will get here. So you need more potential drop. So in total, the considered kinetic your curve will be like this. Okay. So this is the real E cell. Once you apply the current, so if you have current, this E cell when you apply the current. Okay, from here to here. So the higher potential is lower energy. Okay, the higher potential, the lower potential will be higher energy. Okay, so this is the once you apply a current. So the real E cell is you need to consider this thermodynamic curve. E cell, this one, right? Then comes plus cathode activation energy, overpotential, the anode overpotential, and also the solution overpotential. So that is the total E cell will be larger than E cell equivalent. So in electrolytic cell, this E cell always larger than equivalent one. So that is that's in the electrolytic cell. So that is very important. Of course, if you change the current, those values will change. So that depend on the current. So that is the electrolytic cell. So similar, you can extend to a common cell. But so you can see in electrolytic cell, after chemical reaction, once you convert A plus C to B plus D, electron energy, the final state is very low, right? If you want to try this reaction, you need to make a circle, right? Circulate. If you cannot pump this electron back, then the reaction cannot complete. So that you need a pump. So you need a power source. Like you need like a water, you need a pump to pump this water or electron to high energy again, so the reaction can continue. If you cannot pump this electron up, then this reaction cannot complete. So that is electrolytic cell, because you convert electric energy to chemical energy. Okay, so the E cell always larger than the equipment, E cell equipment, because you need more energy than thermodynamic desire. Yeah, and similar you can extend to harmonic cell. So the harmonic cell, the potential is less than 0. So this is the same. So for the harmonic cell, the E cell larger than 0. So for harmonic cell, this harmonic cell. Okay, so again we can draw from the energy. So again, this the diagram you can see from the beginning. So the energy, the higher potential need to be lower energy, and the low potential of the EA would be this low potential of EA would be the higher energy. So because it's a little bit complicated, I draw the same color so that you can. So this original, if this original curve, thermodynamic, the green one is thermodynamically, okay? So the same as here. I'm sorry, this curve is a little bit complicated. Okay, then again is right. Remember, in this case, we want to convert the chemical energy to electric energy. So we are pumping up of the electron energy. So like thermodynamically, you can pump the electron energy to here. But once you have electrochemical reaction, you have some loss. So in reality, you cannot pump the energy. Oh, sorry. So this the this curve is the thermodynamic curve. Okay, so original you can theoretically you can pump the energy to here thermodynamically, but in reality you cannot pump the electron energy, convert the chemical energy to electric energy. you cannot pump to here because you need to consider loss. So this is the loss. Okay? You need to consider, like in the previous case, you need to consider loss. So you can only pump to this potential, this energy. Okay? So you need to consider this loss. This is the loss. Then again, in a solution also loss, right? The energy. The energy also, because you need to conduct so you need to conduct the ion transport. Just similar in the previous case. So in a solution, you also need to consider the loss. So this also loss for the ionic conduction in the solution part. Then you want to convert again from the chemical energy to electric energy at the anode part. So this is thermodynamic. Okay, thermodynamically, you can convert this value. These two values are the same. So thermodynamically, you can convert. However, again, you need to consider the loss for this converging reaction. So this is the loss. Again, this is the loss. Okay? So your final state actually. So if you draw the real condition, the real curve will be like this. Okay? I need to draw very fast. So, okay, then up to here. So this is the final potential. So like this is the final E cell. This E cell equivalent. Oh, of course, this energy is not the E cell. This is only the energy. I should say this is the energy. Only the energy. Thermodynamic energy. We don't call this E cell. Because this in the energy diagram. So that you can we can convert this energy diagram to this potential diagram. So lower potential, then you can convert to lower energy, convert to higher potential, and you need to consider loss. Then in a solution, you also consider loss. Then, okay, if you consider loss, you at this part. Okay, then you need to consider the potential just for thermodynamic part should be equal to this part. Okay? But you also need to consider loss. So yeah, so this is the thermodynamic from here. And this also the thermodynamic, supposedly. Okay? But you also need to consider the loss at the anode part. So that is here. Okay? So this is the loss. We call eta A. This eta C, right? This eta A. So this loss, this is from the solution loss from electrolyte. Okay? Solution over potential. So the potential you have the cathodic over potential, the solution over potential from the solution resistance, and also the anode over potential. So in this case, the E cell, the final E cell, this the final E cell should be from this one minus this one minus this one and minus this one. Then you get the real E cell. So in the common cell, the E cell should be lower than this value. Okay? So lower than this equivalent potential. So, but the energy is larger than this side always. So it's still the reaction still can continue because you convert the chemical energy to electric energy, so you can try this reaction continuously. So the common cell is a spontaneous reaction, but not like this electrolytic cell. Electrolytic cell is not a spontaneous reaction. So yeah, a little bit complicated, but please read again and again. So that is, you can extend some idea from like this dye-synthesized solar cell. So you put the cathode, this is the cathode side, this is the anode side. Okay, of course because it's solar cell, you use light illuminated at this side, at the anode side. And then, like this, you use iodide redox as a mediator. It's a redox mediator. So at the cathode side, this iodine will be reduced to iodide. Of course, this the I3 minus is iodine plus I minus, so that is triple iodide can be reduced to iodide. Then at the anode side, you want to continue this reaction, you need to oxidize this iodide again. So this iodide release the electron. So of course, one you can, if you don't use a dye, you can use, if you just use simple TiO2. Then if you only use this TiO2, of course this reaction can happen. This iodide can be oxidized at the anode side. But with that, because the blanket of the TiO2 is too big, so you only can absorb the radiation energy a very small amount in solar light. So your solar efficiency would be solar cell efficiency would be very low. But once you introduce the dye, like you introduce this dye with a nano blanket, so you can absorb with a nano blanket, then you can absorb more solar energy. So this is the blanket. So depending on what the blanket you have, you can absorb different energy, different amount of energy. Then again, just after excitation, you will form a hole at the valence band. Then this electron can inject to this valence band. Then this reaction, and this is electron pump to the conduction band can inject to the TiO2, then can continue this reaction. So that with the dye, if you design a purple dye, then you can get a higher solar efficiency. So that is the same. If you only draw this energy diagram, then you can understand what happened in this dye synthesized solar cell. For this FTO is a transparent glass, conductive transparent glass. So you can put TiO2, put on a dye on this electrode. You can fabricate this dye synthesized solar cell. It's also kind of electrochemical cell if you understand this reaction. So this is the you can see the kinetic parameter. Although this is a standard rate constant, but you can see the order. Okay, so like this ion reduction, ion 3 product reduction, 10 power minus 8. And if like this Seeber reduction is very fast, so it's just comparative, right? It's minus 8, it's minus 4. So this reaction will be much fast. This is also very fast. So this is also a typical redox we can use as a reference. If you want to measure the potential in a solution, you can use this as a reference because this is very the reaction is very fast. So when the reaction is very fast, we can call this ideally non-polarized electron. If the like this reaction is very slow, that is ideally polarized electron. So one is ideally non-polarized electron. One is ideally polarized electron. So if you look at the curve we mentioned in the polarization curve, this would be the small I0, right? This I0 is very small. This I0 is large. The pink color is just like a ideally non-polarized electron, and then this green color is ideally polarized electron. This ideally polar electron. This ideally non-polar electron. So the curve, so once you are is ideally non-polar electron, then you can use as a reference electron. So we have many reference electrons. You need to choose from this ideally non-polar electron. So this is the some basic terminology. Now we just mentioned equipotential and the open circuit potential. What is the difference? Okay, so open circuit potential only that requires only the net current is zero. Equipotential not only net current is zero, should be at the equilibrium condition, and it changes current density. When you measure at the equilibrium condition, the oxidation and reduction current should be equal, but in a different direction. That equal to exchange current density. Then transfer coefficient. So when you apply potential, this transfer coefficient or symmetry factor just separate, divide the energy to one is alpha C fraction, one is alpha A fraction, impact on the cathodic reaction and anodic reaction respectively. So that is very important. And overpotential is the potential apart from the equilibrium potential. Can be positive if for oxidation, if negative is for reduction reaction. And the charge transfer overpotential, or we can also call activation potential or polarization. That for if the reaction that if you have charge transfer resistance, you need to apply this potential to overcome this charge transfer resistance. That is charge transfer overpotential. And concentration overpotential, although we haven't discussed mass transfer yet, but that is if you have concentration gradient, and you need to have joint force to overcome this concentration or mass transfer resistance or concentration gradient that we call concentration overpotential or polarization. And ohmic overpotential or polarization is the solution resistance. You want to try the ion move transport in a solution, that you need the ohmic overpotential. So if you look at this, if you look at this for gamma cell different from electrolytic cell, you can see and it draw very fast. Okay. Then so that is the final part, right? You see the potential. If you look at here, look this higher potential, but it's going up. But for the electrolytic cell, it's going down. If from higher potential, that is different in a gamma cell and the electrolytic cell. So if you see it carefully, you will see the difference. So we probably would stop here for this kinetic part. We will in the next part part, I will introduce the mod transfer. Thank you. Yeah.